Hello students, welcome back. Let us resume our discussion in section 1. Previously we defined quadratic residue. Remember, let P be an odd prime and let A be non-empty. Non-zero mod P. Then we call A quadratic residue of P if this congruence, x squared is congruent to A mod P, has a solution. If there's no solution, then A is called a quadratic non-residue. By the way, if there is a solution, then we can prove that there are two. And furthermore, they are related like this, plus or minus something, so that we can safely say we have plus or minus square root of A if there is a solution to begin with. Or in other words, A is a quadratic residue. In fact, that's what we intend to prove in 1.3. Let's go ahead. Let's scrutinize this quadratic congruence. X squared is congruent to A mod P. Again, remember P is an odd prime. So not just a prime, but P is 3, 5, 7, 11, 13, 17, 19, and so on and so forth. Odd prime. Then, here's a solution structure. If A is congruent to 0, then we have a unique solution. X is 0 and nothing else. Basically, we are looking at a double root. Now, if A is non-zero, then either we have two solutions or no solution. So if A is a quadratic residue, then there is at least one solution, then consequently two solutions, or no solution if it is a non-residue. Let's prove that. The first line is easier, so let's start from the first line. If P divides A, or equivalently A is congruent to 0 mod P, yes, these two are always equivalent whenever P is a prime, then there's a unique solution, X is 0. It's easy to see 0 is actually a solution. 0 squared is 0, no problem there. Now what if X is non-zero? Then X squared is X times X, and that should be non-zero because there's no way getting 0 by multiplying two non-zero numbers modulo P. Remember, modulo P, there is no zero divisor, no non-trivial zero divisor. So we have it. We have only one solution, double root. X is congruent to 0. Now for the second, let's assume P does not divide A, or equivalently A is non-zero mod P, or still equivalently A and P are relatively prime. These three are always equivalent as long as P is prime. So depending upon which one is more convenient, you can use whatever you want to. Depending upon what is your preference, you can use whatever you want to. I'm going to mix those up. Okay, in this case, suppose that there is a solution. Let's say X is alpha. Then it turns out negative alpha is also a solution. Or equivalently speaking, P minus alpha, because P is congruent to 0 mod P. And these two are incongruent, so we have actually two incongruent solutions. Let's check that. Alpha squared is A, then P minus alpha is also a solution. Well, what is P minus alpha? P minus alpha squared puts 0 in place of P, so negative alpha squared. Oh, that's A. Negative 1 squared is 1, so no problem there. So P minus alpha is also a solution, automatically a solution too. So we have potentially two solutions. Now, are they the same or are they two distinct solutions? Well, that depends upon P does not divide A, or equivalently A is non-zero mod P, or equivalently A and P being relatively prime. Let's see. Let's suppose alpha and P minus alpha are congruent. then p is congruent to 0, so alpha is congruent to negative alpha, and then add alpha to the other side, and we get 2 alpha is congruent to 0. Now here, I can remove 2 by dividing it away. Does it make sense? Can I do that? Yes, it does. Yes, I can, because p is an odd prime. If p is 2, I can't do that. I cannot divide by 2. P is an odd prime, so p is relatively prime to 2. So 2 has multiplicative inverse modulo p, so I can divide it away. Once you do that, you're going to get alpha is congruent to 0, therefore a is alpha squared, so that's congruent to 0. But that's a contradiction because we assumed alpha is non-zero. So what do we have? Alpha and p minus alpha cannot be congruent. They're two distinct numbers modulo p, or they're incongruent. Finally, apply Lagrange's theorem. There are no more. There cannot be any more. So these are the only solutions. We have precisely two solutions, alpha and negative alpha. In other words, square root of a and negative square root of a. The problem is which is positive square root, which is negative square root. That's a bit unclear, but if you accept square root expression as double valued expression, just like the way you do in higher level complex analysis, then no problem actually. So that completes the special case. X squared is congruent to a mod p. Now shall we go back to the general case as a corollary? What is the general case? Ax squared plus bx plus c is congruent to 0 modulo p. In that case, please recall the computation we did. We get this computation. Remember this? And then first equivalence comes from 4a being invertible, and the last line comes from 2a being invertible, and those are both okay because p is an odd prime. Remember? The big problem is this one right here, the square root. Is this valid? And we answered that question just now. If the inside b squared minus 4ac is 0, then we have a unique solution. So this complete square is b squared minus 4ac, and that's 0. That means inside has to be 0. So that leads to a single linear congruence, and we can solve it. Flip b to the other side to get negative b and divide away 2a. We get that. By the way, compare that with our solution. X is negative of b minus 2b over 2a, excuse me. This one here, something we had been using from college algebra days. Remember that? This is part of the vertex formula of quadratic function. X coordinate. Y coordinate, if you plug in that thing to the equation of that quadratic function, you're gonna get that y coordinate. Or there's another one using this b squared minus 4ac as part of it. Anyway, it's gonna be nice to see something going hand in hand with quadratic expression of real number system. Now what if this discriminant p squared minus 4ac is non-zero? In that case, we can have two solutions or no solutions modulo p. If b squared minus 4ac is a quadratic residue, then we have two solutions, plus or minus of some alpha, which I'm gonna write as square root of b squared minus 4ac, and then flip this b to the other side, and then divide away 2a, which is always possible. Then we have this quadratic formula modulo p. And please check that goes hand in hand with our old quadratic formula that's been going on for, I don't know, from middle school at the very least, maybe even elementary school. Okay, we went through all those, so why don't we go ahead and do some example problems. Here's a problem. 5x squared minus 6x plus 2 is congruent to 0 modulo 13. 13 is prime, it's an odd prime, so we can use everything that we did here. Solution 1, quadratic formula method. So we have negative of b plus square root plus or minus square root of b squared minus 4ac divided by 2a. So 2 times a, so that's 10 inverse, and then 6 plus or minus square root of 36 minus 40. Now 10 inverse, that's a bit difficult to calculate, but you can try various numbers. They're not that many because we have only 0 to 12 to consider. It'll turn out 4 is the answer. 10 times 4 is 40, and that's 39 plus 1. So yeah, this is the multiplicative inverse. So we have 4 times. Now 36 minus 40 is, what is 36 minus 40? It's negative 4. But negative 4 is 13 minus 4. So that turns out to be 9. And we know how to calculate the square root of 9. Plus or minus 3. So we have this. 4 times 9, which is 36. So 10 plus 26, so we have x is 10. And 4 times 6 minus 3. So 4 times 3 is 12. Okay, like that. Another way is to use the textbook's method. Get this discriminant first. b squared minus 4ac turns out to be negative 4, which is 13 minus 4, and consequently 9. So taking the square root, we get 3 or negative 3. And negative 3 is congruent to 10 mod 13. So this complete square is square root of b squared minus 4ac, but put this y value directly to get a linear congruence and solve it. We get 10, and from the second we get 12. Of course, the same answer as before. How about the next problem? In this case, this b squared minus 4ac simplifies into 36 minus 60, negative 24, and 26 minus 24, so we get square root of 2, but this is a problem. This expression, square root of 2 expression, is invalid. It doesn't exist. There is no integer from 0 to 12 whose square is 2, and you can check it by brute force computation. Check everything from 0 to 12. You'll see. And the textbook solution actually is the same. You're looking at this b squared minus 4ac, which simplifies into 2 modulo 13, and then there's no number from 0 to 12 modulo 13 whose square is congruent to 2. And here I checked manually, not manually, excuse me, I checked everything with Mathematica, and you can see all false. And then I checked everything for the entire congruence, and then again you see all false. So there's no solution.